So hello, I am Mahammad Kazimzada, and this is my walkthrough of my solution for the homework 2 of Computer Organization and Architecture course. So let's get started without wasting any more time. As you can see, I have all the decoded instruction, all the step-by-step decoded instructions here. I written them all step by step in detail, and for the first part of this video I'm going to explain them one by one, and then I'm going to explain the code, the program itself, which I have here, and explain why it is broken, and yeah, that's it for whole video. So let's start with first instruction. So before jumping into the decoding process, so the key element to decode any instruction in ARM32 is to look at I would say the first 6 bits, because they reveal so many things. The first 4 bits, which is here, so 1110, it specifies the condition at which the instruction must be executed, and the other two, here we have 00, so it specifies the kind of instruction, what kind of instruction it is. And if we identify these two, and the rest of the road becomes easier, much more easier, because and especially if we identified opcode. So if we identify the opcode, then we know what kind of instruction it is, and if we know what kind of instruction it is, then we can pretty much know in which direction is the instruction going. So let's use this idea in each instruction decoding. So we have the first 4 bits is for any ARM instruction, it specifies a condition. So we have 1110, and it says that it means this instruction is unconditional. So it means that this instruction is unconditional, and it will get executed no matter what. And then we have opcode 00. It means it is a data processing instruction. So this is a very useful information for our decoding process. So 00 means it is a data processing instruction, 01 means it is a memory instruction, and then 10 means it is branch instruction. Then then we are sure that this is a data processing instruction, then we pretty much know we only have 3 cases for a data processing instruction. So which I have if you look at the presentation, we can see that okay, this is the data processing instruction. It only has three ways to go. One of them is data processing instruction with an immediate. The other one is data processing instruction with immediate shifted register, and the data processing instruction with register shifted register. So let's analyze this instruction. So every data processing instruction has a funct field. So it's this 6 bytes. So these guys here, 111010. So funct 111010. It has 4 subfields. So immediate, CMD, and S. Immediate, it specifies what kind of immediate specifies whether the value comes from an immediate or it comes from a register. And then CMD, it specifies what kind of data processing instruction it is. So if you look at from the PPT again, so for each CMD value, we have a corresponding name. So for example, for 0100 means it is an add instruction. So, and then S field, it specifies whether this instruction must update the ends and CV flags or not. So so this is the whole point. This is the whole point of funct. So I means the sort of value comes from a constant. CMD, it is a 110 means it is a move instruction, and then S equal to 0 means that this instruction won't modify the ends and CV flags. And then for every data processing instruction we have after the funct we have this destination source register, and in our case it is 000, but we can see that this is a move instruction and for move instruction this field is always going to be 0000 because it is ignored for move instruction, because we don't really need a source register for move instruction. We only need destination register, and we only need destination register and whether the value comes from a constant, from an immediate, or from the register. And then we have here RD, which is destination register. So the destination register here, it specifies to which register do we want to apply the value to at the end. So we do all this calculation, and to which register do we want to let's say store the value. In our case, if you look at the binary sequence of zeros and ones, we have 0 0 0 1, which is which means in decimal it is 1, and so destination register is R1. So and the key thing here is to look at immediate, because it reveals which path is this instruction going to take. So because immediate is 1, we can see that from the slides also, if immediate is 1, it should go to this path. So it should have 12-bit space for two fields, 4 bits for rotation and 4 bits for the immediate for the immediate, which will have 8 bits. So rotation is 0 0 0 0. So no rotation amount is 0, and it means that we don't really need rotation here, because we can specify the number in just 8 bits. And immediate 8, it is 0 in decimal, so it means that the number that a constant that we want to store in this R1 destination register is just 0. So if we decode this whole instruction, it is just this: move R1 0. And so this is for the first instruction, decoding process of this first instruction. And if you look at, so let me do this. If you look at so this looks much better. So if you look at instruction 1, instruction 2, instruction 3, instruction 4, and I don't want to waste time here, because so all of them, they take the same idea. Let's say they are the same. All of them are move instructions. So move instructions with all of them are move instructions with immediates. So all of them essentially take the same path. And the only differences are, or in all 4 of them, are just destination register. So destination register and destination register and the immediate. So that's it. So for instruction 2, it is move R2 10. For instruction 3, it is move R3 0. For instruction 4, it is move R4 5. So let's go to instruction 5. So this is where the things get a little interesting, because we move away from all these move instructions. So again, so the first principle stays the same, so the condition and opcode first, and then the rest is going to be easier. The condition is again, so 1110, which is an unconditional instruction. So this means that this instruction is going to get executed no matter what, no matter the NZCV flags. And the opcode is 00, which means it is a data processing instruction. And then, because it is a data processing instruction, we know that it has a funct field which reveals a lot of things, and we look at it is a 6-bit field. Yeah, so the immediate is 0, so this is new, at least for us, because we only saw 4 move registers. So yeah, it is new for us, and so immediate is 0, which means that the value will come from a register. So we can be sure that our decoding process will not take this path, so it will only take this path here. So it's either going to be a register shifted register or immediate shifted register. And the key idea to identify which path is this decoding process is going to take is really simple. And so if we just have to look at these two values, 0 and 1. So yeah, it just reveals the whole thing, it just reveals the whole picture here. So if the 4th bit is 0, so it's an immediate shifted register. We can see from here. So but if it is a 1, then it is a register shifted register. Let's see in our case what it is. So let's move step by step. So immediate is 0, so it's going to take any of these two paths. Immediate is 0, so CMD is 0, 0, 1, 0. So again, if you look at the CMD values, so what was it? So 0, 0 was 0. It is a subtraction, so it is a sub instruction, and S is 1. S is 1 is that it is going to be sub S instruction. So this instruction will modify the NZCV flags. And so I have a note here. So the 4th bit indicates that this instruction contains an immediate shifted register, not register shifted register. So the 4th bit is 0, and as I said, 4th bit reveals the whole path. So if the 4th bit is 0, then it means the decoding process will take this path. I'm recording, yeah. So yeah, let's move to this. So we have decoded these bits. So we are at this bit. So this bit is source register. So source register is R3 because 0011. If we convert this, it is 2 plus 1, 3. So source register is R3. This is destination register. So destination register is R5. So let me go out of the preview for it. Yeah. Yeah. So yeah, where was I? 0101. This tells us the destination register. So this is going to be R5 because 4 plus 1 is 5 and R5. So as I said, it will take this path. So this is these actually we have to do this. So 0 0 0 0 0. So 5 zeros means this is the amount of shift. 0 0 0 0 0 means it is the shift type. And yeah, so why I do this is that because it takes this path and we have to account for that. So this is shift amount, so it will shift amount of 0. 0 0 is the shift. 0 0 means, so the shift type field has 0 0. It means it is left shift, and the register to shift is R4. So which register do we want to shift? So yeah, if we decode this instruction again, it will be sub S because S is here, sub S, R5, R3, source register, and R4, so register the shift, and LSL 0 because we have to shift it, right? But because there's no shift amount, so we can just omit this and it will be simply sub S R5. So subtract R4 from R3, store it in R5 and update the whole is the CV flags. Then so this is a new instruction here. So again the whole thing here is to this is not, sorry, this is not a new instruction. I thought it's going to be it's going to be by branch instruction, but it is a data processing instruction again. So we have the new thing here is that this is not an unconditional instruction. It is if you look at the binary sequence, this is 1011, which is this. So this is LT. So this is this instruction will get executed if N flag is turned on. So this is basically it. So opcode is 0, this is data processing instruction. So this is the whole funct field. So immediate is 0, value comes from a register. So 0, 1, 0, 0, if you come here and see that what kind of data processing instruction it is, and this is an add instruction as we can see here. And S is 0, so we don't modify the as the CV flags. So because I is 0, we have to know again, so I'm going to explain this again, so that we have to know what path are we going to take. Is it going to be here or here? And because the fourth bit is 0, we are taking this path again. So yeah, destination register, the source register is 0, 0, 0, so R0. Destination register is the same. This means we are going to do add R0, add LT, R0, R0, something, right? So shift amount is 0, shift type is L left shift, and the register to shift is R2. So if we decode this, the instruction becomes add LT, R0, R0, R2, and LSL 0. So basically add LT, R0, R0, R2. So we could even do this, but just for clarity, this is the instruction. And instruction 7, it is also an add LT instruction. So it takes similar approach, but difference here is that the immediate is 1. So the difference here is that we don't have any shift amounts, shift types. We just have source register, which is R3, destination register, which is R3 again, and the rotation amount and the immediate, which is 1. So this is it. For instruction 8, now we are in different territory. So again, this whole idea here is to identify the condition and opcode, and the rest is easy. So condition is 1011, as we saw here. It means LT. So the instruction is only get executed if the N flag is turned on. And for opcode we have 10, which means it is a branch instruction. So we haven't seen it, I haven't explained it, and I will explain it in a minute. So one branch instruction, it is actually much simpler than any data processing and the memory instructions, because it only has limited fields. So let's decode it. So branch instruction. So if we look here, if you find a branch instruction here from the slides, we can see that okay, this is really easy. Just condition up, and we have a small funct field, and the rest is immediate. So this is signed immediate, by the way. Sorry. So this is easy. So if we decode funct field, which is 10, and the first bit is always 1. And the second bit, it specifies if it is a branch BL instruction or not. So this is not a BL instruction, it is just a simple B instruction. So a simple branch instruction with some with the condition here of the BLT. So BLT, and the rest of this is just immediate. So this immediate, it seems like it is a big number, but it is not, because this is a signed immediate. So if we do 2's complement, it will be 0 0. So this will be 0 1 0 1, and if we convert it to decimal, it is going to be, so 4 plus 1 is 5, and it's going to be -5. So this number is just represents that -5. But we don't really do -5, because -5 it means that so -5 doesn't really mean anything. So because if we the idea of branching is to go some number of instructions forward or some number of instructions backward, and each instruction in ARM32 all of them takes 4 bytes. So if we want to represent -5 in the number of instructions, we should multiply this by 4 to let's say represent this as a number of instructions to go forward or backward. So if you do -5 times 4, which is 20, so -20, and we know that the program counter points 2 instructions forward, because we have seen it in the first homework, but I'm going to explain it also, because as this instruction is being executed, the next instruction is being decoded, so the program counter must point to the memory address of the 2 instructions ahead, and this is because of the pipelining. And so if we try to calculate the relative address, we must do PC plus 8 minus the number of instructions. So here, it's not this is not the number of instructions, this is the number of instructions, but we have to turn it into bytes, because each instruction takes 4 bytes. So this is the number of instructions, so 5 times 4 is 20. So PC plus 8 minus 20, PC minus 12. This means that go 3 instructions back. So in assembly, it will look like something like this: BLT PC minus 12, and one might see that we have to go back to some branch. So instead of PC minus 12, we will have a branch name here, and I will show it in a couple of minutes that I have added some branching just for more, let's say, elegant version of the code. And then we have another branch instruction here. So this is unconditional branching. Unconditional branching opcode is 10, and this is called the funct is 11. The first bit is always 1, and L is 1, which means this is a BL instruction. So this is a special instruction, which BL instruction it behaves like a branch instruction, normal branch instruction, plus it will store the address of the next instruction into the link register. So this is what makes BL special. So if you decode the rest, so this is just immediate 24, which is how much do you want to go, how much forward or backward do you want to go. So this is a negative number. If we take 2's complement, it is just -1. And if we do the same procedure that we did here, it is PC plus 8 minus 4. So PC plus 4. This means go 1 instruction forward. So BL PC plus 4. Then we came to a new type of instruction here. So this is a memory instruction. So 110 is, so this is unconditional memories. This is an unconditional instruction, and 01 for opcode means this is a memory instruction. And memory instruction, it is I would say it is simpler than the data processing instruction, because we only have to identify the fields, and then that's it. Because so typical memory instruction, it has I, P, U. So this is going to be, so this is let's do this. This is I, this is I prime. So I prime, P, U, B, W, L. So all of these let's say letters, they all mean something in the background. They all specify the kind of memory instruction, and we will walk through. As you can see, I prime, P, U, B, W, L, it has a bit pattern of 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. Yeah, it is simply that. So I prime is 0, which means that this is a memory instruction with immediate offset. And then for P and W, so this is 1, 1. P and W, it also specifies the kind of memory instruction. So I repeat this word often, but it also is more specifically, it specifies if whether it's pre-indexing, post-indexing, or simple offset addressing. And 1, 1, if you look here, it should be here. Yeah, so 1, 1 is pre-index, 0, 0 is post-index, 0, 1 is not supported, and 1, 0 is offset. So in our case, we have 1, 1, so this is a pre-indexing. So one might suspect that this is some kind of storing the, let's say, link register in the stack pointer. And then we have U is 0. U specifies if do we subtract from the base register or not. So if U is 0, we subtract. If U is 1, we add. So instead of representing the immediate with 2's complement, we can just pretty much do this. So U is 0, so it means that we will subtract from the base. As you can see, U is 0, subtract from the base. If U is 1, add offset to the base. So it's simple, really. L and B, so what kind of, is it a store, is it a load, store, if is it a store byte or load byte? So in our case, we have, I believe, 0, 0, so this is store instruction. And yeah, that's it for I, P, U, B, W, L. And then the rest is simple, because yeah, we have Rn, Rd, and depending on I value, we will go to different directions. And in our case, I is 0, which means that we will just have an immediate. So our job is even more simpler for instruction decoder. So Rn, which is this 1101, it means 8 plus 4 plus 1, which is 13. So R13. So source register is R13, and it is stack pointer. So so we were right. And then destination register is RD, which is 1110. So destination register is this R14. So 8 plus 4, 12 plus 2, 14. So R14 it's a special purpose register, and it is LR, link register. And the rest is easy unsigned immediate. So this is the whole unsigned immediate bit pattern: 0000, 0000, 0100. So this is 4 in decimal. So basically it is this store R14 in R13. Yeah. So because it is pre-indexing, we have exclamation mark here, so to indicate that okay, this is a pre-indexing, and we are subtracting. That's why u is 0, so the immediate is 4, u is 0, subtract. This is a source register, this is the destination register. But actually, in the case of store behaves differently than other ARM instructions. So this is a source register, this is a destination register. So this is a source. So whatever value you have in R14, store it in stack pointer -4. Okay, this is the whole idea of this assembly code. And then we have a move instruction here, which I explained how it works. And then we have a move instruction again, and then we have add data processing instruction, which I explained, add instruction. We have an subtract instruction again, sub s, and then we have a memory instruction. So yeah, I explained it. So unconditional, this is not a BL, it's a normal B branch instruction. This is the 24-bit immediate. If we take 2's complement, it is -7. So PC plus 8 minus 28, which is PC minus 20. So go 5 instructions backward. So once we are done with this, we can take our code, which is here, and I want to check in this video also. So let's go to CPU later. So this is, am I recording? Yeah. So yeah, the only difference here is that instead of let's say instead of PC minus 20, I have here branches. So it's just that, just for the program to have more elegance. Let's say compile and load. Once it is loading, so yeah, if we do compare each instruction, so it is just E3A01000. So all of them matches. So this proves that our decoding process was right. So let's get, I don't want to waste time on checking everything here, because I have already done it. So just copy this, and if one would copy this and add it to the CPU later, it would see that it is correct. So this program crashes. Okay, so the whole idea of this this is the second part of this homework exercise. So this program crashes, and we can see why. And let's look at the first part of this program. Let's look at here. So this is simple move instruction, so it wouldn't crash here. There's no ambiguity or error here. Then we have branch A, and one would expect that maybe this branch is being executed repeatedly, but it is not, because in each first execution of each iteration, let's say we do subtract R4 from R3, subtract R4 from R3, and store it in R5, and then update as a CV flags. And as we can see here, we do 2 conditional instructions and 1 conditional branching, so all of them in the same condition, LT. So if n flag of n and CV, if it is turned on, then yeah, this loop will get this branch will get repeatedly executed. But it will at some point it will stop, and the point is that when R3 because we do add lt r3 r3 1. So once r3 reaches 6, it will be bigger than r4, and we don't modify r4 here, so we can be confident that the error is not here. And once r3 is 6, once it has a value of 6, it will not get this branch will be, the program will just go away from this branch, let's say. And then yeah, let's do compile, or yeah, we do compile. So step into. So we would expect the R0 to have, so yeah, so this will run once the loop will end once once the R3 becomes 6. Yeah, it became it became 5. Yeah, it became 5 because it's not less than. And so this part is not problematic, so this is true. Let's move on to this part, and this is where the problem is. Because we do BL branch B. The first problem here, I will say that why do we do BL branch B, and the link register will take this. The link register will store the memory address of this instruction, and which is essentially if we do BX LR, and we will come back to this place, so we can't really come out of this function. So okay, and let's even forget about it. So BL branch B, we push link register into stack, which is a good sign. We do move R4 15, move R5 10, and then we do add instruction and sub S instruction, and the problem here lies in this line. So we do unconditionally B branch B, and we can see that okay, last instruction, it is unconditional. So we do B branch B. So there's a stack overflow here. We could call it infinite loop, we could call it stack overflow. So in either case, the program will not stop, and at some point it will the stack will reach heap. It will take all the available space that the operating system has given to it. It will take all those spaces, and then after that, operating system will have to halt the whole program, because it will go on. If it does not do that, then it will run forever. So the main problem here is that we do B branch B again, and without any conditional layers. So without any condition, so once the program reaches here, it can come out. And we can see here, I believe, step into step. Yeah, after, so as you can see, there's no way for this to go out of this, for the program to move out of this loop or this branch, this function, because there's no condition to go out. It unconditionally moves back to here. How would I fix it? So that as a bonus, I would say that I would add this, so that I would add this. I would do load register. I'll load into LR stack pointer and 4, and I would do BX LR, and then yeah, this will be solved. And after this function has ended, the program would go back to this, will go back to here, and the operating system will terminate its execution. So yeah, this is my walkthrough of my solution. I have explained all of this, so I might have skipped some, but because the video will take longer and I see that it is already 40 minutes, so I try to explain all the necessary things and try to avoid redundancy. This is the whole code. I explained it through this CPU later, and yeah, that's it. Thank you for your attention and see you soon.